Okay, we're going to talk about implicit differentiation for 2D surfaces. So your Calculus 1 class should have talked about how to find the derivative when you just have some function of x and y equal to 0. I mean, what you do here is you write y as y of x, and so that lets you write the equation as just f of x, y of x equals 0. So now if you apply d dx to the equation, what you should get is f partial derivative in x. So I'm gonna be lazy and just write fx for df dx. I'm gonna write fy for df dy. So for example, if f equals x squared plus y squared over 2, this would be x, this would be y. So fx plus fy times yx equals 0. So that allows you to solve for yx. And again, yx is, I'm going to dy dx. I'm being lazy. If you can make notation that lets you save time, why not? So this gives you fx divided by fy. And this is a sensible result on dimension grounds, because the left-hand side is y divided by x, and the right-hand side is f divided by x divided by f divided by y, which should give you cancellations for those f's, and the y goes on top, hence y divided by x. And so this is sensible. It's a sensible result. So this is for curves, right? And this is, why is it useful? Why do we even need implicit differentiation? Well, one application is arc length of a curve, because you need 1 plus y prime of x squared dx. That is ds, that's the arc length. Well, if we do the same thing in 2D, the surface area of some surface, it turns out it's just 1 plus zx squared plus zy squared. So the only difference is that you just add an extra partial derivative. And so this will be your dA, d surface area, or ds, however you like. But you don't need to know that right now. I'm just trying to explain, why do we even care about implicit differentiation? Well, implicit differentiation gives us derivatives, and derivatives allow you to compute surface area, just like y of x allows us to compute, y prime of x allows us to compute arc length. So let's talk about 2D case. So let's just do the general case first, because sometimes it helps to see this. So if we have an equation that looks like f of x, y, z equal to 0, for example, x squared plus y squared plus z squared over 2 equals 1, or let's just say minus 1 equals 0, just to make it an f equals 0. So this is obviously, let's just get rid of that 1/2. So this is obviously just the sphere. And the question would be, how do you find dz dx, which I'll denote by zx, and dz dy? So how do you do this? What I'll do is, here's a simplified way to write. This is not mathematically valid, but I think it's helpful. So what am I trying to say? I'm saying replace z with z of x if you want to find a zx. And if you want to find a zy, replace z with z of y. So if you do this, then the equation looks like f of x, y, z of x equals 0, and f of x, y, z of y equals 0. And so now treat as a 1D equation. Okay? And so you just ignore y or x. So I'm going to circle in red the variables that we ignore when we're doing each case. So in the first case, I ignore y because we're just looking at z as a function of x. In the second case, I'm ignoring x because we're just looking at z as a function of y. Okay, so let's see how we do this in each case. So the zx case, I write, I'm putting this in quotation marks because this is not valid, right? Z is really a function of x. It's really a function of x and y, but I'm just ignoring this to simplify things. So I'm going to write f of x, y, z of x equals 0. I'm just going to underline the variable that I ignore. And so now I will differentiate in x. So f of x, so just like in 1D, I'll first take the x part, then the z part. So fx plus fz times zx equals 0. So that means zx equals minus fx divided by fz. Okay? In the case that f equals x squared plus y squared plus z squared, that simply gives you minus 2x divided by 2z. So this is just minus x divided by z. Okay, so now let's find zy. By symmetry, it should be minus y divided by z. But let's show this by differentiation. So I'm going to write f of x, y, z of y equals 0. I will again underline the variable that I'm ignoring. And so now you just apply the partial derivative in y to the equation. So f sub y, you pick up the fy and the fz terms. So fy plus fz times zy equals 0. That means if we solve for zy, we get minus fy divided by fz. And if we, again, look to our favorite example, then we just get minus 2y divided by 2z, which, of course, is just minus y divided by z, which is what we expected. Okay? So let us try out a more non-trivial example. I think this equation, xz equals log y plus z, this is pretty tricky. Because in the sphere case, you could just solve for z and just take derivatives directly. But in this case, you can't really do it. You would need something called a Lambert W function. If you want to see something weird, look this up on Wikipedia. Lambert W function. It's pretty crazy looking, but what we're going to do is we're just going to use implicit differentiation to find the derivatives. So the problem is to find dz dx and dz dy. So I'm going to again go case by case. I'm going to write z as a function of x, and if we write that in the equation, it's just x times z of x equals log y plus z of x. So now I'm going to apply the partial derivatives, just like as in 1D, in one dimension. In one dimension, we would just have the product rule for the left-hand side. So 1 times z plus x times z prime of x, or really I'm just going to put z sub x because I'm lazy again. So then the right-hand side, with the logarithm derivative, just gives you 1 divided by the thing inside the logarithm, and then times the derivative of the thing inside the logarithm, which of course just simplifies. We ignore y. Let me just underline what we ignore. So then we get 1 over y plus z times the derivative of z of x, which is just zx. Okay, so now we just solve for z of x, z sub x. And what I'll do is I'll move z sub x to the other side. I'll just write an arrow to indicate that. So z equals 1 over y plus z sub x minus x z sub x. I can factor to give me z sub x times stuff. So now we just divide. So then we get z sub x equals z divided by 1 over y plus z minus x. And if you want to simplify this further, you can, but I wouldn't consider this critical. The point is that we found z sub x. Okay, so now let's do z sub y. And I'm just going to rewrite our equation really quickly. It's just x z equals log y plus z. And so now, because I'm doing z sub y, I'm going to underline x and indicate that I'm going to ignore this. And I'm also going to replace z with z as a function of y. Again, this is not mathematically valid, but it helps me reduce the problem to a 1D situation, which I'm more comfortable with. So now, as in 1D, I'll just apply d sub y. Okay, so x we ignore. I'm going to underline this. So x times dz dy, which is just z sub y. Again, I like my shorthand notation. So the 1 over the logarithmic derivative, that is y plus z of y, times the derivative of the thing inside the logarithm. Okay, so if we simplify that, 1 over y plus z times 1 plus z sub y. All right, and because I'm solving for z sub y, I want to just expand that thing. And now I'm going to move this bad term to the other side. So x times z sub y minus z sub y divided by y plus z. This will be 1 over y plus z. So I will factor into z sub y times x minus 1 over y plus z. Now we're almost done. We just got to divide, and then we're done. Z sub y divided by, is equal to 1 over y plus z divided by x minus 1 over y plus z. So I'm going to just clear the denominators. So then we get 1 on top, and then x times y plus z on the bottom. Notice that these 1's, they came from the 1 over y plus z's. And I just put that denominator next to that x. Okay? That's it. It's as simple as that. We just got to treat it as a 1D situation, ignore that x, ignore that y, depending on what derivative you're taking. Okay, thanks for watching.